Next topic is energy and entropy balance for reacting system. So the form of the energy and entropy balance used thus far remains valid for reacting system. Still, there are some special aspects worth noting. So combustion air and products of combustions are each model as ideal gas mixture. So it is pretty much similar to the one we have in the previous chapter, but in this case we will have more species in the mixture, not a binary mixture. So accordingly, the ideal gas mixture principles summarized in table 13.1, and I copy it on the right side of this slide, play a role. So in this table you can see we use a similar parameter for this mixture. So for example, N will represent the moles of gas, and I is for gas I, and then YI will be the mole fraction of gas I, and then T temperature, P is pressure, and then we have PI as the partial pressure of gas I. This equals to the mole fraction of gas I times the mixture pressure. And then we have U, H, and S to represent specific internal energy, specific enthalpy, and specific entropy. And because we treat this mixture as an ideal gas mixture, then we can apply a similar formula to the one we have in the previous chapter. For example, the internal energy will be the sum of the internal energy from each component composing the mixture, and then this is for enthalpy. So this is once again the sum of the enthalpy from each component composing the mixture. So we have N1 here times H1 with over bar, so it means this specific enthalpy per mole of component 1 or gas 1, and so on. And then because this is ideal gas, the specific enthalpy and specific internal energy is a function of temperature only. For the entropy, it is a function of two parameters. So in this equation, it is a function of temperature and pressure. And then we will use equation 618 to help determining the enthalpy change. So for example, in this equation A, to get the enthalpy, to get the entropy at a P and Pi, we can estimate it or calculate it as Si at T and P. Okay, so T and P minus R with over bar, so it means this is a universal gas constant, times natural logarithmic of the mole fraction. And this mole fraction for gas I is Pi over P. So this is a useful correlation that can be used once again to calculate the entropy of gas I at T and Pi. And then you can see in this equation B, if P equal to P ref, which is 1 atmosphere, then you can see in here on the first term of the right hand side, so we have Si at T and P ref, and this equal to S prime or S degree at T, and this S prime or S degree is available in table A-23 or A-23E, okay, for British unit. And then on the right side, you can see in here you have a similar formula. So you have R with over bar, so this is universal gas constants, time the natural logarithmic of Yi time P over P ref. Okay, so P ref here is 1 atmosphere. So with this equation B, we can estimate the specific entropy of gas I at T and Pi using table A-23 to get S prime or S degree here at the corresponding temperature, and then subtract it by R over bar minus ln yi times P over P ref. So back again to the energy balance here. For a reacting system, the method used for evaluating enthalpy and later on for entropy as well differ fundamentally from the practice used thus far in non-reacting application. So we have started using this enthalpy concept from chapter 3 onward. But when we deal with a reacting system, so we will need to have a special treatment, especially on how to determine the datum of this enthalpy and entropy. So this brings in two new concepts here. First is the enthalpy of formation, and the second one is absolute entropy. And in this chapter 13, we only deal with this enthalpy of formation. So why we need to have this new datum? Let's take a look at this simple example. So the feature on the right side here is showing an open system or a control volume, okay? And then hydrogen and oxygen enters from left side, and then each as ideal gases, and then react inside this control volume to form liquid water. So at the exit we have liquid water, and then at the entrance we have hydrogen and oxygen, and the reaction inside the control volume follows this reaction equation. So H2 plus a half mole of oxygen, and the product is 1 mole of water, H2O. So the schematic of the system is shown again this slide. So to apply an energy balance to the control volume, we might think of using enthalpy data from, for example, steam tables to get the enthalpy for the water. And then also we might need to use table A-23 to get the enthalpy for the gases here, which is hydrogen and oxygen gas here. However, since those tables use arbitrary datums to assign enthalpy value, they must be used only to determine the difference. And we have learned about this one from chapter 3, 4, and so on. So to determine the difference in enthalpy between two states, for then and only then do the arbitrary cancel. So in chapter 3, 4, and so on until chapter 12, so it's mean we don't have a reaction inside the system. So it's mean when the species at the entrance is CO2, for example, or maybe O2, then at the exit it will be still O2 or CO2. So there is no change of the species. Therefore, it doesn't matter we use this arbitrary datum because we deal with the same species and then the same composition, and then this datum will cancel during the calculation of the enthalpy. For the case under consideration, where we have a reaction process inside the system, for example, in this schematic, we have H2 and O2 enter the control volume, but do not exit. So you can see in here on the left side, we have H2 and O2, but do not exit, and liquid water exit, but does not enter. So accordingly, enthalpy difference from inlet to exit do not arise from each of the substance when applying an energy balance to the control volume. So for each, it is necessary to assign enthalpy value in a way that common datum cancels, and this is achieved using the enthalpy of formation. Okay, so once again, this is the idea why we need to use a new datum for this reacting system. So we don't have, for example, just in this simple example, we don't have the same species at the entrance compared to the one at the exit. Okay, so like consideration apply when evaluating entropy value later on for substance in reacting system. And for them, absolute entropy value are also required. And the idea is still the same here. We need to have a new datum that cancel during the operation. A proposed enthalpy datum to the reacting system was proposed by assigning a value of a 0 to the enthalpy of stable elements at the standard reference state. And the standard reference state is at 298.15 Kelvin or 25 degrees C and reference pressure of 1 atmosphere. So any stable element at this reference state will be assigned a 0 enthalpy. And stable element, so it's mean what is the form of the species at this reference condition. For example, oxygen will be in the form of O2, not O. Okay, therefore the enthalpy of O2 at reference state equals to 0, but the enthalpy of single O won't be 0. Okay, because once again single O is not a stable element at reference state. And then the enthalpy of a compound at the standard state equals to enthalpy of formation, denoted by HF with a prime or degree sign here. So the enthalpy of formation is the energy release or absorbed when the compound is formed from its element. The compound and elements all being at T-ref and P-ref. Okay, so this is the definition of the enthalpy of formation. This enthalpy of formation is available in table A-25 and A-25E for the British unit, and it is on a molar basis, so it is kilojoule per kilomole or BTU per pound mole. And the screenshot of the table is shown at the bottom side of this slide. So you can see in the first column it's showing the substance here, and then this is the formula of the substance, and then this is the molar mass, so it's the molecular weight, the M capital. For example, carbon, this is single C here, has the molecular weight of 12.01. And then the next one, this is the enthalpy of formation. So as indicated by the table heading here, this data apply only to the standard state. So this is 298 Kelvin and 1 atmosphere. So back again to this enthalpy of formation column. So stable element at reference state has a 0 enthalpy of formation. Therefore here carbon C has a 0, and then hydrogen has also 0 here, and then nitrogen and oxygen. Okay, and then the next one, carbon monoxide, so CO. Carbon monoxide has an enthalpy of formation of minus 110,000 here, so 530. Okay, and then carbon dioxide has the enthalpy of formation of 393,520 kilojoule per kilomole. Okay, so once again, stable element is assigned 0 to the enthalpy. Okay, and then carbon monoxide, carbon dioxide, and so on has a non-zero enthalpy of formation. So look at the table A-25. You can also find out what is the enthalpy of formation of single O. Okay, just O, not O2. So they have a non-zero enthalpy of formation. Non-zero value apply to all other substance. So where a minus sign correspond to an exothermic reaction when the compound is formed from its element. So positive value for sure, this correspond to the endothermic reaction. So look at back again on this table A-25, we have more data here. So for example, the enthalpy of formation for carbon monoxide and then carbon dioxide, water. So there are two types of water here. One is in gaseous phase, second one is in the liquid phase. So they have a negative enthalpy of formation. This means that the formation of this carbon monoxide or carbon dioxide from its element is an exothermic reaction. And then if you go at the bottom here, so okay, here we have oxygen, single O. It has a positive enthalpy of formation. So it's mean it is an endothermic reaction. And then hydrogen also here, single H. So it has also a positive value here. So it's mean they are formed under endothermic reaction. Okay, we have defined the datum for this reacting system enthalpy. Now we can estimate the enthalpy at certain state. So the enthalpy of a compound at a state where the temperature is T and pressure is P is determined using equation 3.9 here. So H at T and P here equals to the enthalpy of formation plus the difference between the enthalpy at the corresponding state, so at T and P, and the enthalpy at the reference state. So it is H at T ref and P ref. So the enthalpy of a compound is composed of HF, so associated with the formation of the compound from its element, and this can be obtained from table A-25 and A-25E, okay? And then delta H, this is associated with the change in state from the standard state to the state where the temperature is T and pressure is P, okay? So since this term, so delta H, is a difference at fixed composition, it can be evaluated from the ideal gas table, so like table A23, steam table when it is a water vapor, so table A2 or table A4, or other tables as appropriate. Okay, so depending on what is the species there. So if the species is available in table A23, then you can use that table. Otherwise, you might need to use different table. Once we complete this enthalpy of formation concept, now we will apply this to the control volume energy rate balance. So there are two cases here regarding the control volume energy rate balance. One is about the calculation of heating value. This is one of the popular topic in internal combustion engine when we are dealing with the combustion of different fuel and want to know what is the heating value of the fuel. And the second one is the adiabatic flame temperature. So this is the schematic of an open system or a control volume. So we have airflow from the left side at temperature TA, and then this is the fuel flow with a temperature of TF. So the fuel is represented by CAHB here, and then there might be a heat transfer through the system boundary here. So the system boundary is represented by a dash line here, and the system might do a work as well, W.CV here. And then at the exit we have combustion products with a temperature of TP. Okay, this is a control volume system at a steady state, and then by applying the conservation of energy, we can get this formula. So on the left side, we have Q.CV. All parameter here is per mole of the fuel, so N.F here. Or because there is a dot here, then it's mass of, not mass, the mole flow rate of the fuel, so N.F. So the first term here we have Q, and then this one is the work. And then on the right side, the first term on the right side here, we have the enthalpy flow exiting the system. So in this case we have CO2 and then H2O and then nitrogen. Okay, so there might be other species as well, okay, especially when it is not a complete or stoichiometric combustion. And then the second term here, this is the enthalpy of the fuel, okay, and then this one is the enthalpy of the combustion air, so consisting of this O2 and nitrogen. Okay, so now to simplify this equation, we lump the first term on the right hand side here as the HP, so with over bar, so it means it is on a molar basis. So this one is the enthalpy of the product, and then the rest here is the enthalpy of the reactant. So we have air and fuel. Okay, so we can simplify this equation to get this equation. Okay, so you can see in here Q dot CV minus W dot CV, both per mole flow rate of the fuel, equals to HP minus HR. Okay, HP is the enthalpy flow of the product, HR is the enthalpy flow of the reactant. And by applying the concept of the formation enthalpy, so we can replace this HP by enthalpy of formation plus delta H. Okay, similarly we can also replace HR here by the enthalpy of formation of the reactant plus delta H. Okay, so now let's take a look on this example. So we have a pulverized coal, so which can be assumed as carbon, enters a combustor at 298 Kelvin, 1 atmosphere, and burn completely, with oxygen entering at 400 Kelvin, 1 atmosphere. Schematic of the system is showing at the bottom of this slide. So we have a flow of pulverized coal that is represented by a C here at a given temperature and pressure, and then this is the oxidizer, so O2 at 400 Kelvin and 1 atmosphere. A stream of carbon dioxide exits at 500 Kelvin, 1 atmosphere. See here on the right side we have a CO2 at a given temperature and pressure. For a control volume at steady state enclosing the reactor, evaluate the rate of heat transfer in kilojoule per kilomole of coal entering. So assume the ideal gas model for O2, CO2, and neglect kinetic and potential energy effects. And this is the reaction. So we have 1 mole of carbon plus 1 mole of oxygen. The product is 1 mole of CO2. So this is the solution. So the schematic is at the top of the slide. So we have two inflow stream here. One is carbon and second one is oxygen. At the exit we have one stream here. This is CO2. And then the energy balance on a molar basis for this control volume system is showing in this equation. So at the left side we have a 0 because this is steady state, okay? And then we can assume that there is no work, okay, during this process. So it's mean W control volume equal to 0. So this one is 0, okay? And then we have Q dot CV. And then the next one here, this is the inflow energy. So one is from the carbon flow, second one is from the oxygen flow, and this is the outflow energy, so due to the CO2, okay? So once again, W dot CV equals to 0, and we can also ignore the effect of kinetic and potential energy. And then solving for the heat transfer per mole of coal, and noting from the reaction equation that the molar flows are equal. So you can see in here the molar flow are equal. So it's mean we have 1 mole of carbon and then 1 mole of oxygen, okay? So it's mean here when we divide each term of this equation by the number of mole of carbon, then you can see in here that NCO over NC equal to 1, because each term in this reaction equation has 1 mole. And then second one here, NO2 over NC equals to 1 as well here. Okay, so we have this equation to calculate the heat transfer per mole of coal. And then we can simplify the equation as this equation number 1. So Q dot Cv per mole of the coal equals to HCO2 minus Hc minus HO2. Okay, and then carbon enters at standard state. So it's mean delta H for carbon equals to 0 here. Okay, so this one is 0. Okay, and then the enthalpy of formation for carbon can be obtained from table A-25. So the screenshot of this table A-25 can be seen at the bottom of this slide. So we have carbon here, and then the enthalpy of formation for carbon can see in here, this is 0. Okay, so it's mean Hc for carbon is 0, because it's F prime is 0, and then delta F is also 0. Okay, so next one is for oxygen. Okay, oxygen enters at 400 Kelvin and 1 atmosphere. Okay, and to get the enthalpy of oxygen, so we need to know what is the enthalpy of formation and the delta H. So oxygen is a stable component at reference state, so it's mean its F equals to 0, showing here. So the enthalpy of formation for oxygen equals to 0, but because oxygen enters at 400 degree or at 400 Kelvin, which is higher than the reference temperature, so oxygen does have delta H, and we can use table A-23 to get delta H of the oxygen. So this is the enthalpy of the oxygen, so it has a 0 enthalpy of formation. So this is the enthalpy of oxygen at 400 Kelvin, and this is the enthalpy of oxygen at reference temperature, 298 Kelvin. So the enthalpy of oxygen we get here is 3029 kilojoule per kilomole. Next one is to get the enthalpy of CO2. Okay, carbon dioxide exits at 500 Kelvin 1 atmosphere. So the enthalpy for CO2 here is the sum of the enthalpy of formation, and then plus the delta H. So this is the enthalpy difference between the enthalpy at the corresponding state, so 500 Kelvin 1 atmosphere, and the enthalpy at reference state. So CO2 has the enthalpy of formation, and we can get it from table A-25, and you can get the enthalpy of formation for CO2 of minus 393,520. And then delta H here is the carbon dioxide enthalpy at 500 minus the enthalpy at 298, which is the reference temperature. And you can use table A-23. Okay, A-23, go to the carbon dioxide column. You should be able to get the enthalpy of the carbon at 500. So this is 17,678 kilojoule per kilomole, and then the enthalpy at 298 is 9,364 kilojoule per kilomole. Or also in table N23, I think you can also get the enthalpy of formation for carbon dioxide. So you just need to plug in all number here, and you will get the enthalpy of the carbon dioxide at 500 Kelvin 1 atmosphere of minus 385,206 kilojoule per kilomole. So we have calculated the enthalpy for CO2 and then C and O2 Now we just need to plug in all this number to get the heat transfer per mole of the carbon flow. So equation 1 here. Next example, so this is example 13.4 in the textbooks. Liquid octane enters an internal combustion engine operating at a steady state with a mass flow rate of 0.004 pound per second and is mixed with the theoretical or stoichiometric amount of air. The fuel and air enter the engine at 77 degrees Fahrenheit and 1 atmosphere. The mixture burned completely and combustion product leaves the engine at 1140 degrees Fahrenheit. The engine developed a power output of 50 horsepower. So the question is, determine the rate of heat transfer from engine in BTU per second and neglect the kinetic and potential energy effect. Okay, let's take a look on the solution of this problem. So you can see in here we have a liquid octane enter the internal combustion engine. You can imagine this is a liquid gas inside your car engine, and then there will be a combustion there, and then this 50 horsepower you can imagine as the power generated by your car engine to propel the car. And the heat transfer is the energy absorbed by the cooling liquid or absorbed by the airflow through the radiator and so on. Okay, on the left side is the schematic of the system. So here the system is the engine and the system boundary is represented by the dashed line. So we have airflow here at 77 degrees Fahrenheit, 1 atmosphere, and then here we have the fuel flow, okay, so at 77 degrees Fahrenheit and 1 atmosphere as well. And then the combustion product here exit the engine through, let's say, the exhaust pipe. So it is at 1140 degrees Fahrenheit. And then the engine produces 50 horsepower. And then there will be a heat transfer out of this engine. And this is the question. And the assumption, this is a control volume identified by the dashed line here, and it is also at steady state. And then we can ignore the effect of kinetic and potential energy, and the combustion air and the products of combustion each form an ideal gas mixture. And then each mole of oxygen in the combustion air is accompanied by 3.76 moles of nitrogen. And we can also assume that the nitrogen is inert and combustion is complete. So it's mean in the product we only have CO2, water vapor, and nitrogen. The first step, we need to write it down, the stoichiometric combustion reaction for octane, and it is shown in here. So we have 1 mole of octane. It requires 12.5 mole of oxygen and 47 mole of nitrogen. And this is a stoichiometric or complete combustion. We have CO2, H2O, and nitrogen only on the right hand side. So the product is 8 mole of CO2, 9 mole of water vapor, and 47 mole of nitrogen. Next step is to apply an energy balance on this control volume. So we can incorporate assumption 1 through assumption 3. In the assumption 1, we know that this is a control volume at steady state. And then on the assumption number 2, I believe we can ignore the effect of kinetic and potential energy. And then assumption number 3, I think it is related to the ideal gas mixture. Therefore, we can replace the enthalpy with the enthalpy of formation and the enthalpy difference. So here we have this simplified energy conservation equation. So on the left side we have Q dot CV per mole of the fuel. It is balanced by the work generated by the engine and the enthalpy difference between the product and reactant. So W dot CV is given there, 50 horsepower, and then this is the list of the enthalpy of the product. So we have 8 mole of CO2. So here we have 8, and then the enthalpy of CO2 is the sum of the enthalpy of formation plus the delta H, and this one is for the water vapor, and this one is for nitrogen. And then this one is the enthalpy from the reactant. So it's a fuel and combustion air. So we have a 0 enthalpy of formation for nitrogen here. And then we also have enthalpy of formation of 0 for oxygen, and then nitrogen here in the reactant. And then octane, I believe, enter at 77 degree Fahrenheit, which is the reference temperature. Therefore, delta H for octane here is 0. Similarly, air also enter at a reference temperature. Therefore, delta H for oxygen equals to 0, and delta H for nitrogen equals to 0 as well. Okay, so with the enthalpy of formation of octane in liquid phase from table A-25, so we have this one. Okay, and then with the enthalpy for CO2 H2O from table A-25, and then we can use table A-23 to get the enthalpy for nitrogen, and then water vapor and CO. Then we can get the enthalpy of product. So you just need to plug in the number to get this one. So 1,752,251 BTU per pound mole of fuel. And then next one, we need to calculate the molar flow rate of the fuel. Okay, so the mass flow rate is given, I believe. So you need to divide it by the molecular weight of the octane. So it is 114.22. So you will get the molar flow rate of the fuel of 3.5 times 10 to the power of minus 5 pound mole per second. Okay, and then by inserting this number into the energy conservation, we should be able to get the heat transfer from the engine of 22.22 BTU per second. So negative here means that the heat transfer is out of the engine. Next example is to analyze a gas turbine fueled with methane. So in this problem, we have methane or CH4 at 25 degrees C enters the combustor of a simple open gas turbine power plant and burn completely with 400% of theoretical air entering the compressor at 25 degrees C 1 atmosphere. Product of combustion exceeds the turbine at 730 Kelvin 1 atmosphere. The rate of heat transfer from the power plant is estimated as 3% of the net power developed. Okay, so the Q is 3% of the net power developed. Determine the net power developed in megawatt if the fuel mass flow rate is 20 kg per minute for the entering air and exiting combustion product. Kinetic and potential energy effects are negligible. Okay, let's take a look on the solution of this problem, and the schematic is so at this bottom side. So we have theoretical air entering the system at 25 degree C and 1 atmosphere, and it has it has 400% theoretical air amount here. And then this is the flow for the methane, so 25 degrees C, and the mass flow rate is 20 kilogram per minute. And this is the output work of the system through the turbine. And then at the exit, we have the combustion product here at 730 Kelvin and 1 atmosphere. The first step, we need to write it down, the reaction of methane with combustion air. The first reaction here is for a stoichiometric or complete combustion. So in this case, we have 1 mole of methane. To have a stoichiometric combustion, it requires 2 mole of oxygen and 2 times 3.76 mole of nitrogen. And on the right side, we have a CO2 and then 2 mole of water and then 7.56 mole of nitrogen. For a combustion of methane with 400% of theoretical air, so in here we need to put 4 ahead of this mole for air. We need to multiply that by 4, okay? And then because we have more air, so in the product we will have oxygen here, okay? We'll have oxygen. So in this new reaction, we have 4 coefficients that need to be calculated. One is A, and then B, C, and D, okay? And we can fix these 4 coefficients by applying the conservation of mass for carbon, hydrogen, oxygen, and nitrogen respectively. So for example, we can start by applying the conservation of carbon. So on the left side, we have 1 C. So on the right side, we need to have 1 C. Therefore, we fix A here equal to 1. And then the next one here is for hydrogen. So through this conservation of mass for hydrogen, we get B equal to 2. And then next one, this one is for oxygen. And the last one here is for nitrogen. So, and this is the result for parameters here. So A equal to 1, B equal to 2, C equal to 6, and D equal to 30.06. Okay, so once we got all these 4 coefficients, we can plug in the number to get this methane reaction with 400% of theoretical air. Okay. Next step is to apply an energy balance, incorporating assumption 1 through 3. So steady state, we have a 0 here, and then first parameter on the right side. On the right side here is the heat transfer. This is the work, and this one is the enthalpy flow of the reactant, and this one is the enthalpy flow of the product. So since the rate of heat transfer from the power is 3% of the net power developed, we can substitute Q.CV here by this number. So 0.03 W.C. This is negative because the heat transfer is out of the system. So we get this energy balance equation. So on the left side, we only have W.CV over NF parameter. It is balanced by the difference of the enthalpy flow between the reactant and product. So the reaction of the methane with 400% of air is shown at this top right. So now we need to evaluate each term in this energy equation. So methane enter the system at a reference state, and then combustion air also enters the system at a reference state. So it is 25 degrees C, 1 atmosphere. Therefore, delta H for methane, and then O2 and N2 for the reactant side equals to 0 here. Okay, this is 0. And then the enthalpy of formation for O2 and N2 equal to 0 as well, because it is a stable element at reference state. Therefore, this is also 0, and then this is 0. And then in the product side, the enthalpy of formation for oxygen is equal to 0. And then the enthalpy of formation of nitrogen equals to 0 as well. But they do have delta H because the temperature at the exit of the system is above T reference. Okay. So with the enthalpy of formation for CH4 from table A-25, then we can get HR of this one, so minus 74,850 kilojoule per kilomole fuel. And then now we need to get the enthalpy flow for the product. So in this case, we use table A25 to get the value for CO2 and H2O, and then table A23 to get the enthalpy values for CO2, H2O, O2, and N2 at 730 Kelvin and 298 Kelvin. So just need to plug in all number there, and you will get HP of minus 359,475 kilojoule per kilomole fuel. Next one is to calculate the mole of the molar flow of the fuel. So the mass flow of the fuel is given 20 kilogram per minute. So we need to change it to be kilomole per second. So we divide it by the molecular weight of methane. So this is 16.04. And then we need to change the unit 4 times from per minute to per second. So it is divided by 60 here. So you will get the molar flow rate of the fuel of 0.02078 kilomole per second. So we got all parameters in the energy equation here. You just need to plug in and you will get the net power by the power plant here, gas power system, of 5.74 megawatts. So keep in mind, you also need to apply this conversion number because the unit asked in this problem is in megawatt. We have completed the cases for control volume. So now let's take a look on the closed system energy balance. So this is showing an example of a closed system. So you can see in here there is no mass flow rate through the system boundary. So and the system undergoes a thermodynamic process that change the state from state 1 to state 2, and from state 1 to state 2, the system also undergoes a chemical process. So this is the energy balance for a closed system. So Q minus W equals to UP minus UR. Okay, this is a closed system. So there is no energy by the flow, and therefore on the right side we have the parameter of U, not the enthalpy. But you can see later here that you can replace this U by this parameter. So it is H minus R times T. Why? Because in this case, we assume that each component composing this system is an ideal gas. So in ideal gas, we can have this correlation U equals to H minus R times T. Okay, so therefore you can replace this U different by the enthalpy different. So but you need to have, or you need to include this additional term, so R times T. Okay, and this is the final form of the energy equations for a control volume. On the left side we have Q and W. On the right side we have this energy flow, and this is for product, and this one is the energy flow for the reactant. Let's take a look at this example. So this is for a closed system. case, so a mixture of 1 kilomole of gaseous methane and 2 kilomole of oxygen initially at 25 degrees C and 1 atmosphere. So this is at reference state. So burn completely in a closed rigid container. Heat transfer occurs until the products are cooled to 900 Kelvin. If the reactants and products each form ideal gas mixture, determine A is the amount of heat transfer in kilojoule and B is the final pressure in atmosphere. Okay, this is the schematic of the system. So at state 1, here we have 1 kilomole of methane. This is gaseous phase. And then 2 kilomole of oxygen at 25 degrees C and 1 atmosphere. And then at state 2, after they react, so they have a product of combustion at 900 Kelvin and P2. So P2 is one of the question here. And this is the engineering or assumption. So this is a closed system, so a rigid container. So there is no flow rate through or over the boundary of the system. And then we can ignore the effect of kinetic and potential energy. And then combustion is complete. Okay, so this is stoichiometric combustion of methane. And then the initial mixture and the product of combustion each form ideal gas mixture. And then last assumption here, the initial and final states are equilibrium state. Okay, this is the stoichiometric combustion of methane with oxygen as the oxidizer. So 1 mole methane requires 2 mole of oxygen. On the right side, we have CO2 and water vapor. And then next step is to apply an energy balance. So in this case, we consider assumption number 2 and number 3. So there is no work generated during this process, and then this is steady state. So you will get this energy balance equation. And then here Q equal to UP minus UR, okay? And then UP here is the product internal energy, so it has 1 mole of CO2 and 2 mole of water vapor, and then in the reactant we have 1 mole of methane and 2 mole of oxygen, okay? And then since this is an ideal gas, we can substitute U by this one, by H minus RT, then you will get this equation, okay? So then you can collect the term to have this equation. So on the last term of right hand side here we have 3 times R times T1 minus T2. Okay, so you just collect the term with R times T here into one term here. And then you simplify or you replace this enthalpy flow by the sum of the enthalpy of formation and the delta H, okay, here. So this one is for CO2 and this is water vapor, and this one is for the reactant. So you have methane and oxygen. And then methane and oxygen initial state are at reference state, so it's mean delta H equal to 0 here. And then enthalpy of formation for oxygen is 0, this one, okay. And then by using table A-25 to get the enthalpy of formation for CO2, H2O, and CH4, and then table A-23 to get the enthalpy value for water vapor and CO2, then you can calculate Q here, and you will get Q of minus 745,436 kilojoule. The second question is the final pressure P2. So in this case, we can use the ideal gas equation of state. For example, at state number 1, you have this correlation, okay? And then at state 2, you have this ideal gas correlation. So you have in this one you have P1 times phi equal to NR times R times T1, and then at state 2 you have P2 times phi, so it is a rigid container, so it means volume stay the same. And then you have on the right side here we have NP times R times T2. Okay, so once again, since phi stay the same, from this two equation you can get this correlation that P2 equals to T2 over T1 times P1. Okay, so P2 is 3.02 atmosphere. Next topic is enthalpy of combustion and heating values. The enthalpy of formation of fuels is not always tabulated. When it happens, then we can use the enthalpy of combustion to conduct an energy analysis. And this enthalpy of combustion is accessible experimentally. The enthalpy of combustion is defined as the difference between the enthalpy of the products and the enthalpy of the reactants when complete or stoichiometric combustion occurs at a given temperature and pressure. And the enthalpy of combustion is formulated with this equation 13.8. The first term on the right side here is the enthalpy of the product, and the second term here is the enthalpy of the reactants. So this is the enthalpy of combustion, HRP, on a molar basis. And then the heating value of a fuel is a positive number equal to the magnitude of the enthalpy of combustion. So the enthalpy of combustion, it's a negative because the combustion process is an exothermic process, so that the enthalpy value is negative, and then the positive number of this enthalpy of combustion is called the heating value. There are two different value for heating value. One is called the higher heating value, HHV, and the second one is the lower heating value, LHV. So we call it as HHV, or the higher heating value, when the product of the water is in liquid phase. And then the lower heating value is when the product of the water in the combustion product is in vapor or gaseous phase. So the difference between this higher and lower heating value is the heat of evaporation for the water. Let's take a look on this example. Calculate the enthalpy of combustion of gaseous methane in kilojoule per kilogram of fuel A at 25 degrees C, 1 atmosphere with liquid water in the product. Okay, so liquid water. So it means we will have a higher heating value. B at 25 degrees C, 1 atmosphere with water vapor in the product. So it will be a lower heating value. And C, repeat part B at 1000 Kelvin, 1 atmosphere. So this is the engineering model. So each mole of oxygen in the combustion is accompanied by 3.76 moles of nitrogen, which is inert. And then combustion is complete. So it means stoichiometric combustion. And both reactant and products are at the same temperature and pressure. And then the ideal gas model applies for methane, the combustion air, and the gaseous product of combustion. And this is the stoichiometric combustion for methane. So for 1 mole of methane, it requires 2 mole of oxygen and then 7.52 mole of nitrogen. In the product, we have 1 mole CO2, 2 mole H2O, and 7.52 N2. And then using equation 13.9 in equation 13.8, we can calculate the enthalpy of combustion or formulate the enthalpy of combustion with this equation. So this one is from the product and this one is from the reactant, and we replace the enthalpy by these two terms. The first term is the enthalpy of formation, and the second term is the delta H between the enthalpy at reference point to the enthalpy of at the corresponding state. Next step is to introduce the coefficient of combustion equation and evaluating the specific enthalpies in terms of the respective enthalpies of formation. So we have this equation, and then the enthalpies of formation for oxygen is 0, so the 0. And then we don't need to include the enthalpies term for nitrogen because nitrogen enthalpies for reactant equals to the nitrogen enthalpies of the product, so both cancel out. And then by rearranging the term, you will get equation 1. In this equation 1, the value for each Rp prime, which is the enthalpy of formation, and delta H for H2O depend on whether the water in the product is in a liquid or in a vapor phase. Okay, so let's take a look on the question A. So in question A, the reactant and product are at 25 degrees C and 1 atmosphere. So in this case, delta H drop out in equation 1, okay, because it is at reference condition, so we don't have delta H here. Then we can simplify equation 1 to get this equation, okay. So the enthalpy of production, the enthalpy of combustion equals to the enthalpy of formation for CO2 plus 2 times the enthalpy of formation for H2O, and then minus the enthalpy of formation for methane. And we can use table A-25 to get this enthalpy of formation. Then we will get this value. And also in this case we have H2O as a liquid phase. So it means we need to take the corresponding enthalpy of formation for a liquid water. And in this case it is minus 285,830 kilojoule per kilomole. And then dividing by the molecular weight of methane, place this result on a unit mass of the fuel basis. So the molecular weight of methane is 16.04. So we will get the enthalpy of combustion of minus 50,507 kilojoule per kilogram fuel. And you can check with table A-25 that the magnitude of this value agrees with a higher heating value of methane. Okay, so this is higher heating value type because the H2O phase is liquid. And then go to question B. Okay, in question B here, the water is in vapor phase. Okay, so we use the same formula here. Delta H drop out because the product and the reactant are at the reference state. But the difference is that you need to grab the enthalpy of formation for H2O as the gaseous phase. Okay, so in this case we have minus 241,820 kilojoule per kilomole. So after inserting all number, we get the enthalpy of combustion for this methane of minus 50,019 kilojoule per kilogram. Okay, you can see here that it has a lower enthalpy of combustion compared to the result for A. Okay, this is higher heating value and this is a lower heating value. Then you can check this number by comparing it with the lower heating value for methane in table A-25, and both are the same. Okay, and the difference between these two heating value is the heat of evaporation of water. Next question is, what is the enthalpy of combustion when the reactant and product are at 1000 Kelvin and 1 atmosphere? So in this case, the delta H is not 0 anymore. Okay, so delta H will be the enthalpy difference between the reference point enthalpy and the enthalpy at 1000 Kelvin. Okay, so you can use table A-23 to get the delta H for O2 and then H2O and CO2. Okay, so you have two temperature. So this is at reference condition, this is at the current condition. So pick up the correct number for the enthalpy at these two temperature for O2, H2O, and CO2 from table A-23, and you will get this delta H. And then for methane, I believe the delta H is not available. You can use this formula to estimate delta H for methane. In this case, we use CP expression from table A21. So using this one, you can see. And then you just plug in the two temperature here at 1000 and 298. You will get delta H for methane of 38,189 kilojoule per kilomole. So you get all number, you just need to plug into the equation and you will get the enthalpy of combustion at 1000 Kelvin of minus 49,910 kilojoule per kilogram. So you can compare this result with the result from B and you can see that the difference is minor. Next topic is adiabatic flame temperature. To introduce the adiabatic flame temperature concepts, we can consider the reactor at steady state as shown in this figure. So we have airflow from this side and then fuel flow from this side, and there will be a combustion inside this reactor, and then this is where the combustion product exits the system, and we might have a work here, W.CV, and there will be a heat transfer here to the surrounding. So in the absence of work and appreciable kinetic and potential energies effect, the energy liberated on combustion is transferred from the reactor in two ways only. The first one is through the energy accompanying the combustion product at TP here, and the second one is through the heat transfer to the surrounding here. Okay. The smaller the heat transfer to the surrounding, the greater the energy carried out with the combustion product, and thus the greater the temperature Tp of the combustion product. So it makes sense, okay? So if we minimize a Q here, so it means we will maximize the energy with the combustion product. So the adiabatic flame temperature here is the temperature that would be achieved by the product in the limit of adiabatic operation. So it means this will be the maximum temperature. So the maximum adiabatic flame temperature corresponds to a complete or stoichiometric combustion with a stoichiometric or theoretical amount of air. So when we have a stoichiometric combustion and the reactor is adiabatic, then we will have the maximum combustion temperature, and it is called adiabatic flame temperature. Okay, let's take a look at this example. Methane gas at 25 degrees C, 1 atmosphere, enters an insulated reactor. Insulated, so it means it's operate adiabatically, operating at steady state and burn completely. So it means stoichiometric combustion with X time 100% of theoretical air entering at 25 degrees C, 1 atmosphere. So here we have a variable amount of air. So it's X here represent the variable. and then plot the adiabatic flame temperature for X ranging from 1 to 4, and then assume ideal gas model principle apply. And this is the schematic of the system. We have a reactor here. This is a control volume. We have two inflow stream here. One is for the fuel, second one is for the air, and then on this side we have product. So, and then there is no work, there is no Q. Okay, so here equal to 0. So stoichiometric or complete combustion of CH4 with theoretical amount of air is formulated with this reaction equation. So for 1 mole of methane, we have 2 mole of oxygen and 7.52 mole of nitrogen. And in the product, we have 1 mole of CO2, 2 mole of H2O, and 7.52 mole of nitrogen. Complete combustion of CH4 with X time 100% of the theoretical amount of air is shown with this equation. Okay, so we have X here that will be vary, and we need to know the impacts of this X to the adiabatic flame temperature. So for each specified value of X, the evaluation of adiabatic flame temperature requires an iterative solution of the corresponding energy rate balance. So we have the energy in the reactant and we have the energy in the product that need to be balanced, and this can be done by doing an iterative solution to get the appropriate flame temperature. And then applying an energy rate balance at steady state using equation 13.9 to express the enthalpy of each substance in terms of its enthalpy of formation, and then varying X from 1 through 4 yield the plot shown here. And this is the term for the enthalpy equation. So for sure, you need to do an iterative process to get the temperature, and you can see here from the plot, as we increase the amount of air, the adiabatic flame temperature decreases. So it makes sense because we have more air that need to be heated to a certain temperature. So therefore, the overall flame temperature decreases. So once adequate oxygen has been provided to permit a complete combustion, so it means stoichiometric combustion, bringing in more air dilutes the combustion product, lowering their temperature. And we use this method to lower the flame temperature, and by having a lower flame temperature, we'll have less NOx emission. So we use this strategy in the combustion to reduce NOx emission. Okay, we have completed the discussion of this chapter. I suggest you to try solving the analytical problem at the end of this chapter so that it helps you on solving the actual problem in the homework or in the exam.